Center of mass and symmetry. Okay, in your warm-up, you just got out your notebook. Then you made a prediction. If I was just holding out a meter stick and I was wanting to balance it horizontally, where could I hold it with just one finger? Most of you picked the middle, or 50 centimeters. And then I did it. Turns out, in this case, you were right. Okay, so then I had a meter stick with a 200-gram weight taped at about the 97 centimeter mark. So very close to one end. And I made you predict where I could hold that meter stick and balance it horizontally with just one finger. This was a little trickier. So I had guesses that it would be somewhere between 50 and the weight, but not sure where. And then anything between 70 and 95. In fact, when I showed it to Miss Cantrell, she didn't think I could do it. Okay, and then I did it. Turns out the balance point was at about 82 centimeters. So what was the difference between those two meter sticks? Well, it was pretty obvious. There was a weight taped to the end of one of them. So why did that matter? What that weight did was it changed the center of mass. And so it changed where the balance point was. You might hear this referred to as center of gravity, but in this class, those are pretty much interchangeable, and we'll just go with center of mass to all be on the same page. So why center of mass is important is that it makes problems simpler when we assume constant density of something. So even though a tennis ball isn't constantly dense, in fact, it's hollow, and it's not even completely uniform on the outside, but it's close enough. So we're going to assume that we can treat it as a point mass at the center of mass. So when we talk about describing the linear motion of something, so what I mean by that is really anything that's not rotating. Okay, so this could be a ball in a trajectory as well if I threw it. So the center of mass is really what we're going to end up describing with our equations of motion. Also, when we get to forces, the center of mass is what accelerates according to Newton's second law. Don't worry about what that is yet. We'll get there. All right. And when we start talking about two object systems, the center of mass has its own special reference frame that is sometimes useful for solving problems. Okay, so how do we find the center of mass? Well, technically, it's multivariable calculus. But that's only if you have a complicated shape. Or we can use this thing called symmetry. So here, there are 4 shapes. We talked about these in class. So a tennis ball is a sphere. But since it's hollow, technically it's what we would call a spherical shell. It's hollow. All right, so we can use this thing called symmetry that we actually have some intuition for to describe the center of mass as, well, the center. It's in the middle. For the cylinder, all right, we all agreed that the center of mass is, again, at the center. So in this case, you'd have to talk about maybe finding the center of the circle that is the base or the top, okay? And then finding the center of the height, so halfway between the top and the bottom. Okay, for a cube, also in the center, and a 2x4, right? It's got 3 different sizes, length, width, and height. But again, if you take the middle of the height, the middle of the length, and the middle of the width, you find the center, and that's where the center of mass is. Okay, so the next 3 slides about why symmetry is important are partially from a lecture by Dr. Marge Corcoran at Rice University, and she was one of my professors and a pretty cool lady. So we see symmetries in our everyday life, and we can talk about the laws of physics. So even if we don't know them yet, everything in our lives is governed by Newtonian mechanics, what you know as Newton's laws. So they work the same way in the entire universe. If I play pool at my house, or if I go play in Austin, or in Minneapolis when I was at a conference this summer, the laws of physics apply to those balls and the pool table and the cue stick in the same way, no matter where I'm playing. So I can move that pool table anywhere. And the laws of physics, all right, in this case, we say they're invariant to translations in space. Now, you don't have to know all this, but I just want you to see where this fits in. Okay, so also, maybe I want to rearrange my living room, and I move my pool table, I rotate it 90 degrees. Well, the laws of physics are still going to work the same way. So, it doesn't even matter if I rotate the table a lot or a little bit. Okay, so this is what we call a continuous symmetry. And it doesn't matter if I'm playing pool on Monday or Wednesday, or even if Newton had played it when he was writing his laws, or 100 years from now, or when you take your AP test on May 6th. The laws of physics don't change in time. Thank goodness, because I wouldn't want to rewrite my lesson plans every day. Okay, so today was pretty short. The center of mass is important because it simplifies problems, and we're always looking for ways to make things easier. We can find the center of mass using symmetry. Again, looking for those shortcuts to make things easy. Symmetry is a very important topic in physics, and we'll keep coming back to this idea as we go through the course. So there are several types of symmetries: translations, rotations, and with time. And I'm sure you can think of several examples in nature of translational and rotational symmetries, and then anything that doesn't change with time is going to be in that last category.
When people talk about the physics of American
Here's a video
football,
that I
they normally
think
mention
is
force,
kinda cool.
torque, and so on. Like how the energy from two linemen colliding is enough to power a 60-watt light bulb for over a minute, or is equivalent to an average person falling 2 stories off of a building. But there's another aspect of physics in football that isn't talked about as much: symmetry. You might think symmetry is just for butterflies and Rorschach tests, but it's all over the place in football. There's translational symmetry when teams keep the same formations as they move up and down the field, and rotational symmetry when they switch sides after a touchdown. Even the ball has axial symmetry, so it can spin smoothly through the air. But why is symmetry useful in the first place? Symmetry makes things easier, or at least more efficient. It gives you a guide. Same scenario, same action. That means you don't have to reinvent the wheel all the time. To draw a straight line, you just keep drawing in the same direction. For a circle, keep curving the same amount. So when football players practice a play over and over, the patterns of football become so ingrained in their reflexes, they can act without thinking. Psychologists call this habit formation. We call it symmetry in time. And when players line up on the field the same way at the 30 or 40 or 50-yard lines, that's symmetry in space. Even physics itself is symmetric. Ever heard of Newton's law? A body in motion tends to stay in motion? That's just nature saying, keep doing the same thing. What's more, Newton's laws of motion are the same now as they were yesterday, and they'll be the same again tomorrow. Doesn't that make life easy? Ultimately, symmetry is what allows both science and football to function. If the laws of the universe, or the rules of football, changed drastically from day to day, we wouldn't be able to repeat experiments, make predictions, or know what plays to practice. So when you reach for yet another handful of chips while watching the next football game, know that millions across the country are doing exactly the same, in perfect symmetry.
Go Rice!
Five fun physics
here's
phenomena.
another video.
Number 1.
This
have a friend
one,
hold a
please
cane
do
out
not
horizontally
attempt
for
these
you,
at
or another
home.
similar object. And
All
putting
right,
your
I'm
2
actually only
index
going to
fingers
play
together, try
the
to
first
place
one
them
for you that
underneath
relates
the
to what we did
center
in
of
class.
mass.
If you'd like to
When they
find
let
it,
go,
it is on YouTube on
you
the
will find it
Veritasium
doesn't
channel.
normally work. But now try putting each index finger at opposite ends of the cane and then moving your index fingers in towards the middle. What you will find is that they always end up right under the center of mass of the cane. You can try starting off asymmetrically, and they will still end up under the center of mass. You can try going at different speeds, really slowly.
What you will find is that they always end up right under the center of mass of the cane.
Or really fast.
Try starting off asymmetrically, and they will
But you still end up
end up
perfectly under the center of
center
mass.
of mass.
How does this work?
Different speeds.
Number 2, the phone flip. Have you ever tried to spin your phone? If you do it in this direction, it's pretty easy. It stays nicely aligned. If you spin it along its short axis, you'll also find it spins very well. But if you try to flip your phone end over end like this, you can't do it cleanly. The phone will never flip simply end over end without also rotating in one of the other directions. Even when I make an almost perfect flip, instabilities grow until the phone rotates around another axis. Why can't... No, I still can't do it. Why is it so? Number 3. You've probably seen that if you rub a cup on your hair, you can make it electrically charged, and if you bring it close to a stream of water, you can actually cause that stream to deflect. Now, usually this is used in chemistry textbooks as a demonstration of the polar nature of water. Water is a molecule with a more positive side and a more negative side. And so what happens, so you're told, is that the water molecule flips around so the positive side of the water faces the negative side of the cup, and that is what attracts the water to the cup. But this is not the real explanation. If you have a uniform electric field, there's an equal force pulling the positive side towards it as there is pushing the negative side away from it. And so you can't actually do more than just turn the molecules. You would need a really, really strong gradient in your electric field to make this work at all, and it basically is just not going to happen from a cup. So why is the stream actually attracted to a charged cup? That is the question. Number 4, take a piece of your favorite cereal and drop it into a bowl of water. Then, using a very strong magnet, try to pull the cereal around. Isn't that cool? So why is cereal magnetic? And finally 5, the tea bag rocket. Take a tea bag and cut off the sealed end very carefully. Now dump out the tea. Form the tea bag into a square column and balance it on the plate. Now light the top of the tea bag on fire. Try to light it evenly on all sides. Get ready for takeoff. In 3, 2, 1. Ha! Yeah! That is the beauty of the tea bag rocket. So why did that happen? So how do all of these phenomena work? Let me know in the comments, or make a video explaining any or all of them. Or subscribe to the channel and I'll post the answers next week. I hope you enjoyed those fun physics phenomena. I know a guy who would, the former commander of the International Space Station, Commander Chris Hadfield. I'm actually hosting live events with him in late August in Sydney and Canberra. I am so looking forward to that. Now, the Sydney shows are all sold out, but there are still, as of now, tickets to the Canberra show. So if you want to come to that, check out the link in the description. Now, Chris Hadfield actually wrote a book called An Astronaut's Guide to Life on Earth. And I am listening to it right now as I travel around the world, and it is awesome because it contains great advice not only for people who want to become astronauts, but also for everyone who wants to lead a meaningful life here on Earth. And you can download this book for free if you like by going to audible.com/Veritasium, or you can pick any other book of your choosing for a 1-month free trial. Audible is a great service with over 150,000 titles in all areas of literature, including fiction, nonfiction, and periodicals. And so you can find virtually anything you want there. And by going to audible.com/Veritasium, they know that I sent you and they help me out to continue making these videos for you for free. So I really want to thank Audible for supporting me, and I want to thank you for watching.
Okay, so after that, you wrote a reflection of what you learned today, and then we talked a little bit about the test. So this is the last unit, or this is the last lesson out of Unit 2. So if you have any questions over the weekend, please email me. We will have a review on Monday. Have a great weekend.